Hi, I'm Sala, and in this video we are going to start a case study in which we will address whether a given selection of input manipulated variables and output controlled variables is right for a given purpose. We will compare polyhedron tools, exact but only available in steady state, versus singular value decomposition tools, geometry of spheres and ellipses, in a particular numerical case study. In this first video, we will just consider the singular value decomposition approach in steady-state reference tracking problems. We'll assume we have this model with two outputs and three inputs U, which will be considered candidate manipulated variables, and Y will be controlled variables, and then we have a disturbance effect, HD, which will not be considered in this first video. We will assume that this model is a linearization or identification or whatever around this operating point of y, u, and d, and transfer function matrices will be this g and h, but dynamics will be only considered in later videos because for the moment being we will just consider the DC gain in a minute, and only the DC gain of g. Our goal will be achieving a given task without saturating our manipulated variables. So we will assume that this is the hard limits in absolute units of our manipulated variable ranges. First row will be the maximum value and second row will be the minimum value. For instance, manipulated variable 1 will have a range with a maximum of 4 and a minimum of 0. Second one will range between 0 and 1.5, and third one will range between 1 and 2. So, as we are using a linearized transfer function model, we will translate these absolute limits to incremental limits, which are the actual inputs and outputs to my linearized model. So, if I subtract to these absolute limits the operating point, then for instance the first variable, which ranges between 0 and 4, if operating point is exactly at the center, 2, then increments will be from +2 to -2. And second variable, if operating point is 0.5, then available increments will be +1 and -0.5. And likewise, this will be the incremental limits for the third manipulated variable. These incremental limits can arise in practice from saturation, or well, if my process is very non-linear, let's say, maybe my linearized model ceases being valid if we drift away too much from the operating point. So these may be prescribed limits for, let's say, safe operation. Nevertheless, this is an academic exercise, so we are not discussing the reasons or the technology behind these limits. So basically, our goal will be assessing whether, with manipulated variables in these limits, we can move the controlled outputs with enough amplitude to track some given reference changes or to cancel the deviations arising from disturbances. In this first problem, we will just discuss reference tracking in steady state without this saturation, without hitting actuator limits. And in particular, our problem statement will be as follows. My end user wishes to increase or decrease the references from the operating point so that they range in these intervals in absolute units. First row, upper limit, second row, lower limit. So even if the operating point of the first controlled output variable is 9, my user wishes to increase it to maybe 11.6 or maybe decrease it to 8.5. Likewise, the second controlled variable, whose operating point is 1.45, maybe my user wishes to set a set point in 1.6 units as a maximum or 1.35 units as a minimum. Of course, if we are going to operate with the linearized model, inputs and outputs are in incremental variables, so we need to subtract to these limits the operating point, so we get this 2.6 positive increment from 9 to 11.6, or this minus 0.5 negative increment from 9 to 8.5, and likewise the same in incremental units for the second output. So my problem statement is whether I can reach these increments of outputs without hitting these increments of inputs. And I will disregard the time taking to reach them. So dynamics, settling time, or closed-loop bandwidth will not be considered here, and I just wish to answer the question saying whether a step in input within these limits will be able to reach the maximum deviation given by these desired output limits in steady state. So we will discuss only computations with the static gain matrix, which is replacing S by 0, this thing. Good. This can be done by polyhedra manipulation, because the input is a 3D prism and desired output is a 2D rectangle, but that polyhedra manipulation will be left for a second video. In here we will address the problem with the geometry of ellipses, or after suitable scaling, the geometry of spheres and singular value decomposition. So let's do it. The first step is the so-called input and output scaling. In which sense? Well, we will consider a change of variable so that when scaled input and output variables take the value 1, then the increments of inputs and outputs take values at the top of their prescribed ranges. So let us first discuss the output scaling. If I look here to the desired increments as singular value computations and geometry of spheres must forcefully be symmetric around the origin, around the operating point, then I need to choose the worst case as the largest desired increment. For instance, in my first output, maybe the user wants a positive increment of 2.6, a symmetric interval around 0 that contains both extreme points must be plus minus 2.6. So I'll choose 2.6 as my reference point, and I will transform it to being 1. Likewise, in this case, if I wish a symmetric interval around the origin containing both extreme increments, then the set interval must be plus minus 0.15. So it is the maximum of the absolute value, the one that must be chosen from these desired increments. And this is the code. In this way, if I can achieve a scaled increment of 1, the actual non-scaled increment will be 2.6 or 0.15, which will be greater than or equal to the desired increments, whatever its sign. We are in the conservative side. If we now discuss input scaling, then we also need to lie in the conservative side as follows. These are the increments of input that are available to me. Then again, if I use the geometry of ellipses or spheres centered in the origin, the operating point, then the worst case is the minimum amplitude. Let us consider, for instance, manipulated variable 3. What I can assert with certainty is that I can achieve any input increment in the interval plus minus 0.3, but I cannot make a larger interval of admissible inputs while keeping such an interval centered in the origin. So my worst case here is the minimum absolute value 0.3, 0.5, and 2. To stay in the conservative side, saying that for sure my scaled increment of 1 will map to an admissible input. So this minimum absolute value here will set me this diagonal input scaling matrix. So once I have these scalings in the scale variables, my symmetric version of the problem will be that my desired specifications will be reached if I can move the scaled output with an amplitude larger than 1 when my input has an amplitude limit of exactly 1. So once we have translated that scaled input and output problems, the thing we need to do is computing the transfer function matrix, well, in this case just the gain, in these scaled units. So these are the computations. First, from this, we can assert that the scaled output is just the normal output increment divided by the scaling coefficients. Second, my model says that y is GU, of course we are in incremental linearized units. And third, my input in the original units is the scaled input times the scaling coefficients, EU. So this thing is a so-called scaled gain, so that my problem will be solved if the scaled gain maps inputs of size 1 to outputs of size larger than 1. So if we work with the geometry of spheres, size 1 of the input will be Euclidean norm 1. As I said, in the geometry of polyhedron, actual size will be the square of size 1, but in here we will consider just sphere of radius 1, and then that must map to an output set containing the sphere of radius 1. So how do I compute it? Well, it's kind of easy. It's one line of MATLAB. Well, first, if I compute the scale gain, then singular value decomposition gives me the minimum gain and the maximum gain. This means that when the input is a vector of norm 1, the output will have a minimum norm of 1.5 and a maximum norm of 4.4 in the most difficult or the easiest maneuver, respectively. So my unit sphere in the input space totally sweeps the output sphere of radius 1.5, so of course it sweeps the sphere of radius 1, and then we can say that indeed we can achieve the desired output movement within my input limits. A last remark needed when analyzing these things is the condition number. Condition number is 2.9, the quotient between maximum and minimum gain, so it means that computations with this matrix or its inverse will increase relative errors from input to output in a factor of 3, and this is somehow deemed acceptable in usual rules of thumb. Let's say that conditionings below 5 are reasonable in many applications. So in this case, we end the video here stating that we indeed can solve our problem of moving the desired variables in a desired range or even more while not hitting hard limits on my manipulated variables, because the minimum gain is 1.5 in scaled units, and we can do it with sensible robustness guarantees given that condition number is 2.9. So we can achieve any size 1 output increment with an input increment with size Euclidean norm equal or below 1. In a sequel video, we will draw spheres and ellipses that are implicitly being considered when doing this singular value and norm computations. And we'll stop here for brevity. Thanks for watching.